In this video, we're going to look at finding the exact values of special angles in triangles. We need to know the exact value of sine theta and cosine theta for 0, 30, 45, 60 and 90 degrees, and know the exact value of tan theta for 0, 30, 45 and 60 degrees. What we're going to do is look at filling out this table. As you can see here, I've put graphing video for 0 and for 90. I certainly think the explanation of 0 and 90 is easier to see if we do it with a graph. So what we're going to do in this particular video is focus on 30, 45 and 60 degrees. Let's first define sine, cosine and tangent, or if you like, sin, cos and tan. So if we have the sine of the angle, and we will say that this is going to be theta, the sine of the angle is going to be the opposite over the hypotenuse. If we look at the cosine of the angle, or cos theta, this is going to be the adjacent over the hypotenuse. If we look at the tan, or the tangent of the angle, we can say tan theta is equal to the opposite over the adjacent. So let's go ahead and look at that in a triangle. So if I draw up a right angle triangle, we will have something that looks like this. So with my right angle triangle, if I put the right angle here, and I put that this one right here is going to be the angle theta, relative to the angle, we could say now that this is the opposite, this is the adjacent, and this is the hypotenuse. So when we're talking about our trig ratios, sine, cosine and tan, the sine of the angle is the opposite over the hypotenuse, the cosine of the angle is the adjacent over the hypotenuse, and the tan or tangent of the angle is the opposite over the adjacent. So let's go ahead and look at finding the special values or exact values for these special angles. What I'm going to do is start off with an equilateral triangle. If I have an equilateral triangle, I'm going to now give this side length of 2. So this one is going to be 2, this one is going to be 2, and this one is going to be 2. We know that each of these angles will be 60 degrees, so that is 60, that is 60, and that one right there is 60. What I'm going to do is go ahead and split this in half. I'm going to draw it to the side to make it slightly easier, and we will have now half of an equilateral triangle. So this is my right angle triangle. What we'll have is the right angle just here, and I will have this angle right here. This of course is still 60. This one right here is going to be 30, as we've got half of this particular angle. This will be 2, and this will be 1. What we need to do is find this length right here. What we're going to do is use Pythagoras' theorem to find that. We know that the sum of the squares of the two shorter sides will be equal to the square of the longer side. Or if you like, a squared plus b squared will be equal to c squared. So what I can say here is that this length, and I'll just call this x for now, x squared plus the 1 squared will be equal to 2 squared. So I can say now that x squared will be equal to 2 squared minus 1 squared, which is going to give me 3. And we can say now that x will be equal to plus or minus the square root of 3. So as an exact value, the height of this particular, now it's become a right angle triangle, or was an equilateral triangle, is going to be root 3. And that is what we call a surd. It's an exact value. So if you put this in a calculator, and we found the root of 3, let's pop that in. The root of 3, let's do root of 3, that gives us about 1.73, and it goes on and so on and so forth. So what we're now going to do is look at finding now the sine, the cosine, and the tangent of 30 degrees. If I just look at this now, and we take the 30-degree angle just here, relative to that angle, this is going to be the opposite, this is going to be the adjacent, and of course this one is going to be the hypotenuse. So what I'm going to do is start off with the sine of 30 degrees. So if I look at the sine of 30 degrees, we're going to have now the opposite over the hypotenuse. So we can say that is going to be 1 over 2, or if you like, 1/2. If we now look at the cosine of 30 degrees, using exactly what we've got just here, the cosine of 30 degrees, we know that that is going to be the adjacent over the hypotenuse. Well, the adjacent is √3 and the hypotenuse is 2. Finally, we have the tan of 30 degrees. The tan of 30 degrees is going to be the opposite over the adjacent. So the opposite is 1 and the adjacent is √3. We can write this as 1 over √3. If you pick up a textbook, you might see this written as √3 over 3. The reason that is that the denominator of this fraction has been multiplied by √3 to rationalise it. So if I wrote it now as 1 over √3, my calculator will give it as √3 over 3. So what we can say is either it's 1 over √3 or as a rationalised fraction, √3 over 3. So we can go ahead and fill that out. So all I've done here is simply chopped up this equilateral triangle into a right angle triangle. We found this height right here and we've used our trig ratios, so car tower if you like. So what we've got then is this will be 1/2. This is going to be √3 over 2, and this is either going to be 1 over √3 or as a rationalised fraction, √3 over 3. Okay, whilst we still have this particular triangle up, what I'm going to do is swap this over. So what we're now going to do is focus on the 60-degree angle. Relative to that 60-degree angle, we need to change now the opposite and the adjacent. The hypotenuse obviously remains as it's the longer side opposite the right angle. Relative to this 60-degree angle, we have now the adjacent just here and the opposite just here. So what that's going to allow me to do is look at the sine, the cosine and the tangent of 60 degrees. So sine of 60 degrees. Well, if we now consider the sine of 60 degrees, that is the opposite over the hypotenuse. So what we'll have is the √3 over 2. The cosine of 60 degrees, well, we know again that is the adjacent over the hypotenuse, and that is going to give me 1/2. What you might recognise here, and this is what we're going to focus on in the graphing, that these signs have switched. Essentially what we have here is the property that the sine of x, or the sine of theta in this particular case, is equal to the cos of 90 minus theta. And of course, the cos of the angle, or cos x, or cos theta, is sine of 90 minus that angle. And again, we will look at that when we come on to the graphing. Let's finish off now with tan of 60 degrees, so tan 60. Tan of 60 degrees. Well, this time we want the opposite over the adjacent, so it's going to be √3 over 1, which of course will just give us √3. So let's go ahead and fill this table out, and we end up now with the sine of 60 degrees is √3 over 2 as an exact fraction. Cosine of 60 degrees is 1/2, and tan of 60 degrees is √3. Don't be tempted in an exam to just write, well, it's √3, so what I'm going to do is write that it's going to be 1.73. This is what we call an exact value. We leave it in surd form rather than truncating it. So there we go. We've just looked at finding the sine, the cosine and the tangent of 30 and 60 degrees. What we need to do now is look at 45 degrees. What I did here was use an equilateral triangle and split it in half. What we can do on the next one is use a square. Now, if we used a square, what we would end up with, and I'll draw a square to begin with. Let's look at a square. And what we're going to say is for side lengths, and we'll do it with this, we'll say that the side length of this square is going to be 1 by 1. If I now redrew half of this square, what we would have now is an isosceles triangle. So let's go ahead and do that. And that looks relatively, well, it's okay. It's not brilliant, but it just gives us some idea of what's going on. So now what we'd have is 1, 1. This angle right here is going to be 45 degrees, as we simply now chopped the square in half. The right angle remains here, and this one too is going to be 45 degrees. What we're going to do is look at the length of the diagonal. Again, using Pythagoras' theorem, we can say that a squared plus b squared is equal to c squared. So 1 squared plus 1 squared is going to be equal to this length right here, which I could call y, so that's going to be y squared. So we're going to have 2 is equal to y squared, and we can say now that this will be the positive square root of 2. So we say that this length is root 2. So what we're now going to do is go ahead and look at finding the sine, the cosine, and the tangent of 45 degrees. Well, the nice thing here is that we've got both of these being equal to 45. So what I'm going to do here is say that this angle right here, which is easiest to see, relative to this angle right here, this is going to be the opposite, this is going to be the adjacent, and of course the longer side in the right angle triangle is the hypotenuse. So what we're going to do is look at the sine of 45 degrees, so the sine of 45 degrees. We've already established that the sine of the angle is the opposite over the hypotenuse. Opposite over hypotenuse, that's going to give me 1 over root 2. Again, if we put this into a calculator, we're going to get a rational fraction. So if I type 1 over root 2, this is going to give me root 2 over 2. So if you see it in a book as root 2 over 2, root 2 over 2 is the same as 1 over root 2. All that's happened here is that the numerator and the denominator has been multiplied by root 2, so we have a rational denominator of that fraction. Okay, cosine of 45 degrees. Perhaps you've already spotted that this is going to be exactly the same. Remember, what I did, and I didn't really want to introduce this, and we'll look at this at another point, the sine of the angle, sine x or sine theta, is equal to the cosine of 90 minus that angle. And of course we can say that the cosine of the angle, cos x, is equal to sine of 90 minus x. So as expected, we're going to get the same value as we got 45 and 45. Alternatively, if you're not comfortable with that, you can simply say that it's going to be the adjacent, so relative to this 45 degree angle, the adjacent over the hypotenuse, which again is 1 over root 2, which will give us root 2 over 2. Tan of the angle, now let's look at tan of 45. Nice little result this is, and hopefully you can see now that this is going to simply give us now opposite over the adjacent, and that is going to give us 1 over 1, which of course is just 1. So there we go, let's pop those in, and we've completed our table. So we would have now the sine is going to be 1 over root 2, or we could say root 2 over 2, exactly the same here, 1 over root 2, or root 2 over 2, and finally we've got 1. So there we go. We've looked at using triangles, in particular an equilateral and an isosceles triangle, to find the exact values of these special angles. So that's an introduction. It's one way of finding them. In another video we will look at graphing the sine, the cosine and the tan functions and start discussing 0 and 90 degrees for each. 90 degrees for tan is not actually on or in this particular course, but interesting nonetheless. So there we go, these are our exact values for special angles using right angle triangles.